Welcome everyone. Today I will prove you guys the equation that you see on the board right now, which is the equation for the sum of all squares starting from 1 and going to a number n, and that is given by this formula. Now here on the left side we have sigma notation, which is just a shorthand way of writing the following. It is saying 1 squared, and I know it because it says we have k squareds and we are going to sum them. This sigma means that, summation, it stands for that. And it says that k starts at 1, so we have 1 squared, then it is going to increase 1 by 1. So it is 2 squared plus 3 squared plus 4 squared, on and on and on, until we have n squared. So this is what it means. It is just a shorthand notation to showing this sum. And I am claiming that this sum can be represented like this. Now this is very neat and it would be very useful if it is true. So how can we go about proving this to be true, or we could even disprove it? But you will see that this is actually true. So the way I want to prove this is by using a method called induction. It is mathematical induction, to be specific, and the way it works is you think of it as a row of dominoes, okay? You have these dominoes, and I know I am very bad at drawing. Maybe you have these things, and if one of them falls, it will hit the other one, and it will trigger it to fall as well. So this one will fall and this one will fall, and if we have a row of all dominoes, then all of them will fall if only one of them falls. I know this is very abstract right now, but I will specify what I mean. And actually, let me be more clear now. So the way we do mathematical induction is we say if a given statement, if the statement is true for n, if it is true for n, then we want to show that it is also true for n plus 1. So that is where the domino analogy comes in play. It comes in handy, because if this is the nth domino, we know that if it falls, then n plus 1 will fall as well. And well, if we take this as n, then n plus 1 will be this one, and it will fall again. So that is kind of the idea behind this analogy. And how can we use this to actually prove the given statement? Well, to start with, we first need to find an n. We will find a number that the equation that I have just written is correct. So let's see if the equation is correct for 1. What I mean is, if we have this, does it equal the formula? Does it equal the formula? Well, let's see. What should this sigma notation be equal to? Well, it is saying start at 1 and add the squares until 1. Well, it is just 1 squared, so it is 1. And what does the formula tell us? Well, the formula tells us to substitute for n. In this case, we have 1, then we have 1 plus 1. Then for n, we have 2 times 1 plus 1, all divided by 6. So we have 1 times 2 times 3 divided by 6, which is, of course, equal to 1. So it appears that our formula works for the case where n is equal to 1. But does it work in general? So does it work for n plus 1 if it works for n? And that is what we are going to do now. So let me open a new page. To be specific, we now want to show if, I will call it formula, if formula true for n, we want to show that it is also true for n plus 1. Which means if the formula is true for n, we can say that where k starts at 1 and goes up to n plus 1, and we're adding k squareds, this should be equal to, by the formula, this should be equal to n plus 1. And notice I'm just writing n plus 1 instead of n, right? We had n here, and now I'm writing n plus 1. So for this n, I will write n plus 1, which will make it n plus 2. n plus 2. And for the other parentheses, I will write n plus 1. So we have 2n plus 2 plus 1, 2n plus 3 over 6. Now, this is what we want to show. We want to show if the formula is true for n, then it should be true for n plus 1 as well. And the formula being true for n plus 1 means, simply means that this relation is satisfied. So is this relation actually true if the formula is true for n? Well, let's see. Let's start with the left-hand side and try to arrive at the right-hand side. So I am writing the left one more time. K squared. Now, using the definition of sigma notation, we can separate this sigma like this. Like this. Right, this just means add the squares starting from 1 until up to and including n plus 1. And this is just saying add the squares starting from 1 and up to n. You are missing the square of the n plus 1 term, so just add that one as well. So we can do this. And this is where, if formula true for n part, this part comes in play. If it is true for n, instead of this thing right here, we can write n times n plus 1 times 2n plus 1 all divided by 6. So we got that out of the way, and for this one we will just write it. But I want to have a common denominator, so I will just multiply by 6 and divide by 6. And I like that we have a 6 in the denominator, because here we have a 6 as well. So this is a good sign. And we now need to manipulate this this expression, and we will check if it is equal to this thing in the red. So how could we do this? The way I would do it is, I would notice that we have an n plus 1 term here. So I would factor out n plus 1, because it is a common factor. And I would also take the 6 out as well. Now we have n plus 1. Then what is left in the parentheses? We have n times 2n plus 1, right? This and this. Then plus 6 times n plus 1. Notice that it isn't squared anymore because we factored out one of the n plus 1s. And if we expand this, what we have, let's see. Oops. We still have n plus 1. Now inside we have 2n squared plus n and 6n plus 6. So we have 2n squared plus 7n plus 6. Great. And now I want to factor this term. I want to factor this part. How can I factor it? Well, if you think a little, you can say this is 2n and maybe a 3 here and a 2 here. And yes, it would work. So let's go with that. We will have, again, n plus 1 divided by 6. And then times, we have 2n plus 3. And then n plus 2. If we rearrange this, we can say it is equal to n plus 1 times n plus 2 times 2n plus 3 all divided by 6. And this is exactly the same thing as this red part. So we have shown that if this proposed equation, the one that we started with, if it is true for n, then it is also true for n plus 1. So what we have shown is, and I will write it here, we said that if the nth domino falls, then it is guaranteed that n plus 1 will also fall as well. And we also have a starting domino. We said that, hey, look, the first domino will fall. It is true for, the equation is true for it. So if this is 1, then 2 will fall. But now we can think of the 2 as the new nth domino, right? If it is the new nth domino, well, then this one is a new n plus 1. So 3 will fall, so 4 will fall, so 5 will fall, and so on. It goes to the infinity. Every single domino, every single positive integer will satisfy this equation. So in other words, we have proven this equation. It is correct that if you have the sum of all the squares that you can abbreviate using this notation, then you can simply find the sum by substituting for n in this equation. I hope that this video was helpful. Understanding this concept might be tricky if you don't know anything about mathematical induction, if you just got introduced to it, because I am aware that I skipped over those parts a little fast because it wasn't the main the main focus of this video. But I hope that it was helpful. If anyone would like, I can make a whole bunch of other videos about mathematical induction, going into the theory of it, how it actually works, and I can make other videos about proofs using mathematical induction. For example, we could make a proof for the case where k is not squared but it is cubed, or you can try it out yourself as well, and you can do it for k as well without any power. Anyways, I hope this video was helpful. If you have any comments, please write them in the comment section below. Hope to see you in another video. Until then, take care.